Okay, we're going to start on homework 2, part 2. So the first question is, using differential energy balance, explain and derive the heat diffusion equation for cylindrical coordinates. So I already started here with some of our diagrams. So here I just have a section of hold on, let me turn on my do not disturb quick. Did that go to my, okay, cool. So, we have a cross section of a cylinder here, and I have our sections of Z to DZ on the left, and then on the left here, and then I have our theta to d theta on our axes here, and I have our r to dr, which I have here, which is also the same here. I just wrote it up here because I think it's a little easier to demonstrate where exactly that is. And then some equations I have is our energy stored, our energy generation, and our net heat. Just to get us started and kind of simplify some of the things I'm going to talk about. So what we're going to start with is some of our linear approximations. So we can start with, let's just start with z dz over here, over on the left here, and then we'll kind of get into more of the other two, which are pretty similar but just slightly different. So I'm just going to do q plus dz, or sorry, qz dz. So we're going to have qz dz is equal, so this is going to be equal to qz plus z over z. Cool. And then we can, oh wait, I forgot our dz here. And then we can kind of simplify this more and do our q net z, because we're going to need our q nets for all of these areas. We're going to get qz minus just this value we already have. Oops. qz plus d qz dz, and then I keep forgetting this dz. Jeez. Okay, and then we can simplify these terms out and just get our q net z equal to what we have left. Okay. And then, of course, our next step is to sub in Fourier's law. So after we add Fourier's law into our equation, we're going to be left with, let me write this quick, negative k r d, right? No, sorry, theta. Because r always has to stay with theta in this circumstance. dz. And then we can simplify this again. So let me just write an arrow. QNet. I'm trying to keep everything nice and organized because this can get really confusing really fast. D Z T squared. I don't know why I wrote that small. Stop recording. Okay, everything's good. Times our area, which is r d theta d z dr. Okay, cool. So that I'm just going to underline this so I can find it easier. That's our q net for our z. Looks good. So we can move on to our other surfaces. So let's do q, what do we want to do next? let's do R, Q net R. This one's a little simpler than some of the other, or the theta, at least in my opinion, I think. So it's going to be really simple, or it's really comparative to our RDZ. Excuse me. So I'm just going to skip some steps quick. And then just multiply by our area again, as above. And then R is needed in this case just because it changes with position. And we need that. So that's going to be our Q net R for this question, and then our Q net theta is going to be a little more our Q net, let me put this lighting up there, that's better. Our Q net R is going to just be a little not Q net R, our Q net theta is going to be a little more intuitive, take a little bit more work. So what we have here now, let's write Q net theta. Sorry, I'm kind of out of it today, spazzing. Have what we always start with, our d over d theta, or d variable. Going to be similar to the z, but more values, dz, dr. Yeah. And then we just need our constant as above, but again we need r because we need a unit of length in this circumstance. So we need to multiply by r and add our theta because our theta is in radians. So we need a length to multiply by for this to work. So that's why we added r. And then we're going to simplify as we've done with d, or not d, as we've done with z. So we're going to get k 1 over r, so I'm just going to do k over r. D squared t over d theta. Yeah, d theta squared. And then just multiply by our area again. Okay, cool. So let me underline, so we have that. And then I'm going to just copy these down just so we have them to answer our next question. But what we're going to do now is just add these equations into our energy balance and add that into our energy balance just so we can get the whole derivation, and then we'll start working on part 2 using our thermal resistance and electrical equations. Okay, so I'm going to quickly hop into this because this is hard to remember, but starting with our energy balance, we're going to get rho C dt dt, and then we're going to have our area, I need d, I'm already forgetting stuff, d theta dr dz, and that's going to be equal to all of these combined, which we can pull out a k. So we're going to get a k pulled out, and we're going to get d squared t dz squared. Yeah, this is supposed to be squared. I don't know what this doing. D dr. I'm just double checking everything while also trying to go fast. dt. Oh my gosh, dr. Sorry, I'm rushing. R dt d theta dr. Oh my gosh. Plus 1 over r d squared t d theta squared times our area, r d theta d r dz. Is that right? Okay, I think that's right. I'm gonna I'll come back after and make sure this is correct. Okay, so I'm back. I was just double checking something, and I'm glad I did because I missed some stuff. So I just forgot an r here. So let me just move this over, and I'm gonna add this r here. And then I got flustered while I was trying to remember stuff, and added an extra variables. So that's our final answer here. And now what we can do is we can start simplifying terms. So we can see that we can cancel these areas out, and then we can also divide terms over to solve for dt, or temperature gradient. So we can divide by rho c, and this will just be our alpha, our thermal diffusivity. Looks good, so we can move on to the next step. So let me just rewrite this quick so we can see this easier. Alpha. Try to write it a little cleaner too so it's easier to read. Okay. So that would be our final, and then we just have to remember to add our heat generation, so we have to add Q dot. Well, since we divided by rho C over here, we have to remember to carry that simplification over on here too and add our Q dot divided by rho C. That's just for part 2, just disregard that for now. But yeah, that would be our final answer for part A. So that just answers our question of explain and derive the heat diffusion equation for cylindrical coordinates. So now we're going to go into part 2, which is simplifying that equation when there is steady state, no heat generation in heat flow, only in radial direction, to yield an expression for equivalent thermal resistance analogous to that in electrical circuits. So that's our answer for A. And then while I took our cut, I added this just to help us out. So steady state, no heat generation, no flow in radial. So for steady state here, we're going to have our left side of the equation equaling 0. We're going to have our heat generation as 0. And our heat flow is also going to be, or since we only have heat flow in radial, our other positions are going to be equaling 0. And then I also wrote out our voltage equations, which is V equals IR and delta T equals QR, where R is all our thermal resistances. And then here I just have an area of a cylinder, assuming height is 1 because it makes it easy. So we can move on to writing out. So let's simplify everything above. Why not? This will help. Copy this down. Okay, so this, as I said, will go to 0. So dt over d theta will go to 0, 0. Q is 0, so this will go to 0. And d squared t over d. That will get a 0. So what we're left here now is 0 is equal to alpha, or not alpha, 1 over r d dr r dt dr. Okay, cool. So our first step to solving this next problem will be to integrate. So integrate, which will be 0 is equal to dr this is a d dr no, oh my gosh, getting flustered again, dr, and then quantity stays the same. Okay, looks good. And then we can simplify r dt oh my gosh, dt dr plus constant integration g's. Okay, that looks good. And then we need to integrate again. Yeah, we need to integrate again. So what we're going to get now is dt dr equal, hold on, wait, let's get rid of that and we'll simplify. No, we'll keep this, and we'll get dt over dr as c1 over r1, which is t r. Sorry, I'm just trying to go off memory here. And then this is where we get the natural log. R plus C2. Okay, I kind of remember where we're at now. I'm going to drag that over here. And then we need to solve for both of the radiuses, the inner and the outer. So I'm going to call, I'm going to call this one T1 and T2 for the two different radiuses. So let's solve for T1 quick. So we'll get T1 is equal to C1, where'd it go? Oh, it's above, I forgot. ln R1 plus C2. We'll get T2 equal to C1 natural log R2 plus C2. Okay, that looks good. Still recording. Okay, cool. So then we need to combine these terms, so let's combine those. We'll get T1 minus T2 is equal to C1 natural log R1 plus C2 plus, or minus C1 ln R2 plus C2. And then you can see these will cancel. So we'll be left with T1 minus T2 is equal to C1, and then we'll use one of our logarithm rules here. Minus C1. No, that's it. No, because the C1 is just in front of our combined logarithm. And then we need to solve for C1 which is just going to be T1 minus T2 over the natural log of these. Okay, cool. And then we need to plug that into our original C1 in our equation. So C1 what am I doing? T1 minus T2 bruh, that's every time. And then we'll get natural R. Okay, cool. And then this is where our voltage equations come in. Voltage EQs. So we're going to apply Fourier's law for Q equal negative K A. And our area is 2 pi RH, so we'll have 2 pi R, and we're going to just, area is not a thing. Or not area, height is not a thing because we're making it 1. So R 2 C1. Okay, cool. And then we got to add our C1 back in. So we'll have negative, let me add Q again. Q will be equal to negative K2 pi T1 minus T2 natural log R2 R1. And then this is equal to our delta T. So we need to solve for that to find our voltage equation, or delta T. So we'll have delta T, once we solve for that, will be Q natural log 2 R1 over the value out front. And then we'll re-add this H in, even though we pretended it doesn't exist, but we're adding it when it needs to be added. And that will be equal to our resistance equivalent, or equivalent resistance. So that kind of answers that does answer our part 2 for simplifying in the specific case in electrical circuits to yield an expression. So hopefully that answers the question well enough.